Welcome to this learning session on how to cut costs with process analysis and process improvement, where we will learn how to analyze and improve processes and effectively reduce operating costs. We'll find out how to increase capacity with minimum investments, how to increase productivity and cut manpower costs, how to reduce inventory and make our processes leaner and meaner. We will learn how to benchmark processes, compare key performance indicators, and choose the best process configuration that would meet your goals. We shall also learn various process concepts and metrics, their similarities, differences, and application. Let us now start to learn how to analyze a process. Suppose we have a basic process consisting of 5 workstations, each run by an operator. The output of one workstation becomes the input of the next. The process flow indicates the direction the units flow from start to finish. Similarly, the value stream shows how value is created or added sequentially during the processing of the units. A process is made up of several workstations, each of which consists of several tasks to be performed by its operator. A set of processes can form a process chain, sometimes called supply chain or value chain. The same principles in analyzing and improving a process can apply to any set of tasks, workstations, or chains. The first concept we will learn to describe a process is its cycle time. The time a workstation or process can produce a unit of input is its cycle time. Cycle time is also the interval of time between 2 successive outputs coming out of a workstation or process. It's easier to imagine cycle time as the time you have to wait for the next output. Let's go back to our sample process. Suppose the first workstation A needs 2 minutes to process a unit of input. This is its cycle time, or the time to perform all its tasks to produce its output. Here we assume each workstation can only work on 1 unit at a time. The cycle times of the other workstations vary from 1 to 5 minutes, as shown here. By knowing the cycle time, we can now determine the capacity of a process or workstation. If workstation A needs 2 minutes to finish a unit, then it can produce 30 units in an hour. The number of units a workstation can process or complete per unit of time is its capacity. Capacity is just the inverse of cycle time. The shorter the cycle time, the higher the capacity. Workstation C, having the longest cycle time of 5 minutes, has the lowest capacity of 12, while D, having the shortest cycle time, has the highest capacity. How do we get the cycle time and capacity of our process? The answers depend not only on workstation cycle times, but also on the number of operators we assign. Let's take the simplest configuration. 1 operator is assigned to do all the tasks in the process. Since he can't take in a new input until he has finished one, he can complete only 1 unit every 15 minutes, which is the sum of the workstation cycle times. This is the process cycle time for 1 operator. The process capacity then becomes 4 units per hour. At this point, let's learn 2 more important process concepts: processing time and lead time. Processing time is the sum of the cycle times of all workstations. It represents the total value added by the entire process and can be a basis for costing a product or an order. When there is only 1 operator performing all the tasks in all workstations, the processing time is also the process cycle time. Lead time is the processing time plus any waiting time between or inside workstations. It is the time it takes for an input to go through the first to the last workstation, or the total time it was inside the process. In practical terms, it may represent order processing time. In our example, since every unit flows from one station to another without any waiting, lead time is also the processing time. This is not always the case, and more often than not, lead time is longer than processing time because of unnecessary waiting time due to inefficiencies. Next, we would like to find out the lead time if we have multiple operators. Let's try to answer that by following a particular unit, here colored red, from the time it enters to the time it exits the process. As you can see, the lead time or processing time is still 15 minutes. An important rule to remember in analyzing any process is that the lead time of any unit doesn't change regardless of the number of operators in the process. Every unit will have to pass through every station and spend the same time there regardless of who or how many are handling that station. We will go back and clarify further this principle in the latter part of this learning session. What about the process cycle time and capacity in case there are multiple operators? Unlike with one operator, the answers are not obvious from the process flow you can see here. We have to first understand two more concepts to find out the answers. These are the process bottleneck and throughput rate. Everybody is familiar with the real bottleneck, the narrowest part of the bottle that restricts the flow of liquid. Another familiar bottleneck is the narrowest section of a busy road that slows down traffic. Similarly, the workstation, wherever it is inside the process, with the longest cycle time or lowest capacity, is the bottleneck. Here we see that the slowest workstation C is the bottleneck. A process can have one or more bottlenecks if they have the same long cycle times. The next concept we will learn is throughput rate. The actual rate a process or workstation produces outputs is its output rate or throughput rate. The maximum throughput rate of a process or workstation is its capacity. Let's now see how the bottleneck or throughput rate will decide the process cycle time and capacity. Let's observe our process as it moves from the transient to steady or stable state. That is, from the time it begins to operate at the start of the day, empty of units, to the time it is mass-producing at a stable, steady rate. Assuming unlimited supply of inputs, operator A will initially and likely accept and process 30 units per hour, his maximum capacity. He will pass these on to B, who can accept only 20 per hour. So work in process or waiting customers will build up between the stations at the rate of 10 per hour. Similarly, B will pass on to the bottleneck C 20 units per hour, and work in process will build up at the rate of 8 units per hour between them. C will produce only 12 per hour and pass these on to D and then to E. There's no work in process waiting between C and D and between D and E. But D and E won't be able to maximize their capacities because of C's limited output. After some time, B will tell A not to send more than what he can handle, and A will slow down to the capacity of B. Eventually, B will tell A not to send more than what C can process, which is 12 per hour. At steady state, all 5 stations will be producing in sync with the bottleneck capacity. Another characteristic of a stable process is that its input rate, that is the throughput rate of the first station A, will equal its output rate, that is the throughput rate of the last station E. To conclude, at steady state, the process capacity and cycle time are set by the bottleneck station. In this example, the final cycle time of the entire process is the steady state cycle time of the last station E, which is 5 minutes per unit, which makes the process capacity equal to 12 units per hour. In our previous example, we said the bottleneck is the slowest part of the process. In cases, however, where either demand or supply is limited, the bottleneck may not be inside the process. When demand and supply are unlimited, process capacity may be limited by factors such as man, machine, or method. Process bottlenecks may be caused by an unskilled operator, slow and reliable equipment, or complex, time-consuming tasks. There may be cases in which an inadequate supply of inputs or materials may be the one that would limit process capacity and output. Or it may be constrained by limited market demand or orders. Therefore, process capacity is determined by its bottleneck workstation capacity, supply rate, or demand rate, whichever is lowest. Let's take a look at an example. If we have unlimited supply and demand, we saw earlier that the slowest station C, or bottleneck, determines the output rate of the process. If only supply is limited, and we can produce as much as we can with unlimited demand, the supply or supplier becomes the bottleneck and decides the output. In case demand is limited, but not supply, the bottleneck and output rate shift to the take-up rate of the market demand. Let's now learn how to measure the productivity and efficiency of processes with the concept of capacity and direct labor utilization. Improving or increasing utilization is a key to cost reduction since you try to maximize the use of resources, especially labor. Capacity utilization is the ratio of throughput rate to capacity. 100% is the maximum. The difference between capacity and throughput rate is idle time or lost capacity. In our previous example, we saw that the output or throughput of every workstation, except the bottleneck, is less than its respective capacity, resulting in low utilization. In this example, we shall assume a labor-intensive process, such that capacity is determined by direct labor, not equipment. Capacity utilization is therefore the same as direct labor utilization. As expected, bottleneck C has the highest or 100% utilization. The rest or non-bottleneck operators and workstations would have idle capacity. You can also get direct labor utilization of each station by dividing its cycle time with the process cycle time or bottleneck cycle time. We use cycle time to get the overall process utilization. Note that to produce a unit, the entire team of 5 operators work a total of 15 minutes or the sum of their cycle times. But each of them actually spent 5 minutes on every unit, which includes idle time due to waiting for the bottleneck C to catch up. In reality, the team spent 25 minutes of direct labor time per unit. So the direct labor utilization of the entire process is the ratio of the total time worked to the total time spent by the team, or 60%. You can also interpret this as on average, every operator only works 60% of his capacity. A more convenient formula to help us compute the direct labor utilization of any process is lead time divided by the product of the process cycle time and the number of operators. Remember, we have 5 operators, each working with the same process cycle time of 5 minutes. This slide gives us another picture of utilization. Note that 40% of manpower is wasted on waiting, not because anyone wants to wait. The line imbalance simply forces them to slow down. So unless you analyze your process well, don't conclude right away that your idle employees are just lazy or trying to avoid work. Next, let's find out the utilization of our process if it's run by only one operator. Lead time stays at 15, and we saw earlier that the cycle time in this case is also 15 minutes. So the direct labor utilization is 100%. This is always the case for any one-man operation, since he is always the bottleneck, and bottlenecks are always busy working. They wait for no one. Before we move on, let's first review our understanding of cycle time and lead time. To reduce cost and time, it is important to know the critical difference between the two time concepts. If the world were a baby factory, its current capacity is 300 babies per minute, with a cycle time of 0.2 seconds per baby. But the lead time or processing time of every newborn baby is always 9 months. As world population increases, capacity will increase, but lead time will remain the same. Next, let's see what happens when you reduce cycle time and lead time. Let's first try reducing cycle time and see what happens to our capacity and lead time. Our process capacity in our previous example is 12 units per hour. Suppose by improving the efficiency of our bottleneck operator C, we can cut the cycle time from 5 to 3 minutes. Since the bottleneck now shifts to station E, our capacity increases to 15. Consequently, we've also cut the lead time from 15 to 13 minutes. The principle is that reducing the bottleneck cycle time always increases the capacity of the entire process and reduces lead time. While reducing cycle time increases capacity, cutting lead time will not always increase capacity. Let's see how this is so. Suppose through re-engineering, we realize that station E is unnecessary, and we can completely take it out of the process. Lead time is cut to 11 minutes. But note that the bottleneck is still station C, which means that our process capacity stays at 12 units per hour. The principle is that if lead time is reduced by cutting or eliminating non-bottleneck operations, process capacity will not increase. One practical insight we get from this lesson is, in general, to increase capacity, production volume or sales, just reduce the cycle time of the process by reducing the bottleneck, while to reduce order processing time or to cut inventories and work in process, cut lead time. You also cut lead time to reduce queuing time of customers inside service factories, thereby improving customer satisfaction. Next, we shall learn how manpower planning and staffing decisions can affect capacity, utilization, and productivity. Let's examine again our 5-man process with an hourly capacity of 12 units. Suppose we add another operator to station A, thereby reducing its cycle time to 1 minute and doubling its capacity to 60. Since the station C remains as the bottleneck, the process capacity remains the same at 12 units per hour. Increasing the number of operators of a non-bottleneck workstation will not increase overall process capacity. Without process analysis, you may inadvertently approve requisitions for additional staff from non-bottleneck departments in your company. The result will be overstaffing without any increase in output or capacity. Back to our original process. This time, let's add another operator to bottleneck station C. Note that its cycle time is cut to 2.5 minutes and the bottleneck shifts to station E, now with the longest cycle time of 4 minutes. Process capacity now goes up from 12 to 15 units. The principle is that adding more operators to the bottleneck workstation always increases process capacity. You may wonder how two operators can work together in one workstation. There are two methods, the non-sharing or parallel method and the sharing method or sequential method. Let's examine the first method. Here you set up a second workstation that's exactly the same as station C. Each one, let's call them station C1 and C2, will have an operator and a 5-minute cycle time. The new station C, made up of substation C1 and C2, can now work on 2 units at the same time. Its capacity per hour will be the sum of those of the 2 operators working in parallel, or 24 units per hour, which is equivalent to a cycle time of 2.5 minutes per unit. Let's now look at the sequential method. Here the 2 operators will share equally the tasks within the workstation C. Station C1 performs the first set of tasks, then passes the unit on to station C2, which does the second and final set. Since station C has a 5-minute cycle time, C1 and C2 will each have a 2.5-minute cycle time. Note that unlike the first method, the new station C here can accept only 1 unit at a time, but both C1 and C2 will always be busy working on 1 unit each. In other words, Station C will now have 2 units inside at any time. It will output 1 unit every 2.5 minutes and therefore have a capacity of 24 units per hour, as in Method 1. So whether you use Method 1 or 2, the new cycle time and capacity will be the same. You may have noticed in both methods, each unit will still undergo 5 minutes of processing in Workstation C, just like before when it had 1 operator. The workstation lead time is not affected by the number of its operators. This process of constant lead time becomes clearer if we redraw our process using Method 2. Notice that every unit will still have to go through 15 minutes of processing even after we added an operator to the process. Though lead time is constant, utilization can improve by adding manpower. With a faster process cycle time of 4 minutes and with 6 operators, here we see that direct labor utilization goes up from 60% to 62.5%. From this slide, we can see that the team, though bigger now, is more busy and more productive than before. To conclude, through process analysis, we've learned that increasing bottleneck capacity may result in a larger percentage increase in overall capacity. Let's now learn the concept of line balancing. Notice that because of the differences in the workstation cycle times of our process, everyone is forced to slow down to the 5-minute cycle time of the bottleneck, and utilization drops to only 60%. What if we can distribute equally the 15-minute lead time among the 5 operators? Our ideal cycle time would be 3 minutes per station or operator. Our balanced line or process would look something like this. So without changing the process flow, lead time, and manpower, and just by balancing the line, we have achieved the following. We have reduced cycle time to 3 minutes. Note that everyone is now a bottleneck. We have increased the capacity to 20, and more importantly, we have increased utilization to 100%, which is always the case when the line is balanced. The key is to break down every workstation into tasks and redistribute these tasks among the available or assigned personnel such that each station will get a cycle time as close as possible to the ideal cycle time, which in this case is 3 minutes. Redistributing the tasks to balance the load may be difficult and challenging, but it may be worth the effort given the huge benefits of a balanced line. Let's say demand this time is limited and you don't want to increase capacity, but you still would want to balance the line to increase utilization and cut manpower costs. Let's see how this is done. First, let's remove all operators and start reassigning them. We bring back 1 operator to work on the bottleneck station since we want to keep the 5-minute bottleneck cycle time so as not to change capacity. Note that stations A and B can be combined to 1 station with a 5-minute cycle time, so we assign another operator to handle both. The same is true with stations D and E, so we call back another operator to take care of both stations. We have actually created a balanced line with 3 workstations, call them A', B', and C', with just 3 operators, each working with exactly the same cycle time of 5 minutes. Let's summarize the results of this line balancing. Lead time remains at 15 minutes. Cycle time remains at 5 minutes, and capacity remains at 12 units as before. What is significant is that utilization is now 100%, like that of the 5-man balanced line we had formed earlier. Finally, without any reduction in capacity or output, we have cut manpower and manpower costs by 40%. Often companies downsize or right-size without really reducing costs. One practical lesson from this last exercise is a key concept of lean management to avoid this mistake. We call it right-sizing the right way. From this slide, note that what we did was assign full work of 5 minutes to all 3 operators A, B, C. to run the three new stations A', B', and C', thereby leaving the two remaining operators D and E completely idle or available for redeployment elsewhere. If we just reduce everybody's cycle time without totally eliminating his working time or idle time, it's not possible to right-size or downsize because all five would be needed to complete the process lead time. In right-sizing, the key is to make an operator completely idle or completely busy. This is what happens after right-sizing the lean way. Our process running with only 3 operators. It becomes obvious and easy to remove the 2 completely idle operators D and E and assign them to some other processes. Another important concept in manpower and capacity planning is takt time. Takt time is relevant in case demand is limited or if there is a buyer's market for your product. Improving utilization and productivity is not the only reason to balance the line and right-size manpower. We also do this when we want to match demand and capacity. In a demand-constrained situation, you would want to match the demand rate with your capacity and throughput rate. This demand rate can be translated into a required process cycle time called takt time. Takt, a German word originally associated with music, means the music beat or rhythm that, say, a conductor uses to guide the orchestra to produce the desired music. In a process, when the takt time is equal to its cycle time, there is a perfect match between demand and capacity, meaning there are no unserved demand nor excess capacity like manpower. Let's look at an example. If demand is 4,800 units per month or 20 units per hour, assume 30 days per month or 8 hours per day, then the takt time is 3 minutes per unit. Let's now apply this takt time to our original process. As you can see in this slide, the process cycle time or bottleneck cycle time of 5 minutes is longer than the 3-minute takt time. This means our process, as it is, can't meet the demand rate of 20 units per hour. Its capacity is just 12 units per hour. To meet the takt time, you may have to adjust your manpower and balance the line. We will now learn how to get the required manpower to meet the demand and avoid overstaffing or understaffing. The required or minimum number of manpower in a process is its lead time divided by the takt time or required process cycle time. In our previous example, the takt time is 3 minutes per unit. Since the process lead time is 15 minutes, the required manpower comes out as 15 divided by 3 or 5 operators. You may be wondering why our process has the right number of operators, 5, and despite being right size, it can produce only 12 units per hour, and not the required capacity of 20 per hour. To right size the right way, we have to do something else aside from having the right manpower. We also have to balance the line and load everyone such that each gets a cycle time of 3 minutes to achieve a process capacity of 20 per hour. Let's take another case. Suppose demand is only 2,880 per month or 12 per hour. Our takt time becomes 5 minutes. Since our lead time is 15, then the required manpower is 3. Let's now try to meet this takt time with our process. Note that though our process can achieve the takt time of 5 minutes and the required capacity of 12 per hour with 5 operators, it will be overstaffed by 2. To right size and achieve the required capacity and takt time, we assign only 3 operators, as in our previous example, so that each gets exactly a 5-minute cycle time, which is also the takt time. To further understand our process and its efficiency, we now look at the concept of work in process. Work in process is the average number of units inside the process, being worked on or waiting inside or between workstations. This would also represent the number of customers inside the service factory being served or waiting to be served. Work in process is actually inventory inside the process, to differentiate it from outside inventory, like those waiting to get inside the process, like raw materials, or those that just got out like finished goods, waiting to be taken by the next process or sold. To find out the work in process of any process, we will use Little's law, named after John Little, who provided its mathematical proof. Little's law simply states that the work in process is the throughput rate or output rate of the process times the process lead time. Little's law applies only to stable processes or those in steady state. As we have learned, a process is stable when its input and output rates are the same or stable. We've seen earlier how a process moves from transient to steady state. Let's examine our original process, which is an unbalanced line, and find out its work in process. Here, throughput rate is 12 units per hour, and lead time is 15 minutes. So its work in process equals 3 units. This means our 5 operators are working on just 3 units at any one time, and these 3 units would most of the time be in the 3 slowest workstations, B, C, and E. Recall that the utilization of this process is 60%, which we derive by dividing the lead time by the product of the cycle time and number of operators. We can also come out with the same result if we divide the work in process by the number of operators. Some may find it easier to understand direct labor utilization this way. 5 people working on just 3 units makes it 60%. Let's now apply Little's law to our balanced line of 5 operators and find out its work in process. Here, throughput rate is 20 units per hour, but lead time is still 15 minutes. So its work in process equals 5 units. This means our 5 operators are working on 5 units or 1 each. It is clear to see that utilization here is 100% because everyone has a job to do all the time. Also, in a balanced line, it is easy to remember that the number of operators is always equal to the number of work in process. Let's see the other variants of Little's law. From the formula work in process equals throughput rate times lead time, we can also derive the following relationship. Throughput is equal to work in process divided by lead time, and lead time is equal to work in process divided by throughput. By knowing any 2 variables, we can always figure out the third. Let's take a practical application. Suppose your friend, here wearing red, enters a service factory like a clinic or a bank. How long would you have to wait for him outside? If from your vantage point, you can see through the facility and counted there are 45 customers inside when your friend went in, and with your watch you estimated that 3 customers come out of it every minute, then you reckon, using Little's law, that your friend would come out after 15 minutes. Let's have another situation. Suppose this time you wanted to find out how many people or customers there are inside the service facility. What you know from experience or from official sources, it should take only 10 minutes to serve a customer. With your watch, you also estimated that 5 customers are coming out every minute. Using Little's law, you're confident to say there must be around 50 people inside the facility. Finally, before we leave this topic on work in process and Little's law, let's learn some ways to cut work in process. Your boss may ask you to reduce work in process to cut costs, namely holding costs such as cost of storage and cost of money. Or maybe he just wants you to reduce the clutter in the plant and free up some space for more productive use. One thing you would not want to do is hide the work in process before your boss arrives. Little's law will help us do it the right way. From the formula, we can see that we can cut work in process if we can reduce either throughput rate or lead time or both. The choice depends on your other goals and which one is easier to reduce. In general, lead time is the harder of the 2 to reduce. If your process is currently overproducing, then all you have to do is to reduce the throughput rate to match the TAT and therefore cut work in process. In case your current throughput rate is already enough to meet the demand, and you don't want to cut or increase production, You have to cut lead time to reduce work in process. Lead time can be reduced using reengineering or value stream analysis by eliminating unnecessary steps or tasks. Just be sure that when you cut lead time, throughput or process cycle time is not affected. In a balanced line, this is unlikely to happen, since even if you remove any workstation, the process cycle time and the throughput will remain the same since every station is a bottleneck. In an unbalanced line, you have a chance of cutting lead time by reducing or eliminating the bottleneck. The bottleneck may shift to a faster station, and you end up unintentionally increasing your throughput rate, resulting in an increase rather than decrease in work in process. Finally, if nothing stops you from reducing both throughput rate and lead time, feel free to do so, and you can reduce work in process much faster. So far, we have learned many ways to change or improve the process. Benchmarking will help us put everything in perspective, organize our results, and compare various processes configuration and process improvements, and find out which ones would help us achieve our goals faster. The key to benchmarking is the selection of the key process metrics and comparing them on an apple-to-apple basis. Let's now benchmark 5 of our process configurations. Case 1 with 1 operator, Case 5, our original base process with 5, Case 5B, our balanced line with 5 operators, Case 6 with 6 operators, and Case 3 with 3 operators. Let's compare the results of our process analysis. First, their process cycle time, throughput rate or process capacity, lead time, which is the same for all, work in process, which we just discussed, direct labor utilization, idle time, which measures unused capacity. Note that utilization plus idle time is always 100%. Output per person per hour, a useful measure of productivity, which we get by dividing the throughput rate by the manpower. Direct labor cost per hour. This is the hourly labor rate times the manpower. Here we assume the hourly rate is $20 per hour per person. And finally, the bottom line of process improvement, the direct labor cost per unit, which we get by dividing the direct labor cost per hour by the throughput rate. Note that we get the lowest unit cost when the lines are balanced and direct labor utilization is highest. You may want to include the holding cost of work in process to make your cost comparison more accurate. Let's now try to improve our benchmarking data to get more insights and conclusions faster. Suppose we make our original Case 5 the base case and index all its metrics as 100. The base case is the situation before any improvement or changes in the process. Let's then index the other processes relative to our base case. With these index benchmarks, we can easily compare process performance and results. For example, let's compare Case 5 with Case 6 and assess the improvements after we've added an operator to the bottleneck station C. We can see that by increasing manpower by 20%, we've cut the unit cost by 4%. At the same time, we increased capacity and work in process by 25% and utilization and output per person by 4%. It is now easier to decide whether increasing manpower this way was a wise and effective decision. Let's now compare Case 5 with Case 3, our lean and balanced process with 3 operators. By reducing manpower by 40% and redistributing the workload equally, we have reduced unit costs by 40%. There was no reduction in capacity with this downsizing, and work in process remains the same. What is significant is that we have improved utilization and productivity by 67%. Let's now look at what perhaps was the most difficult process improvement, Case 5B, where we kept the 5 operators and balance the line by spreading out the workload. This improved process has a unit cost 40% lower, a capacity 67% higher, even though we didn't change the manpower and labor costs. While work in process increased 67%, we have improved utilization and operator productivity by the same percentage. With benchmarking, it's easier to do the cost-benefit analysis of any process improvement or investment. To complete our process analysis, we shall learn the two types of production planning, the make-to-stock and the make-to-order systems. The make-to-stock method of production produces before demand is realized or before orders come in. This system builds goods based on capacity or forecast, which more often than not are greater than current demand. This is the reason stocks are made, only to be stored and hopefully sold at some future date. What are the major reasons to use the make-to-stock system? When processing lead times are long, when capacity is limited, when there's little or no variety in output requirements, as in commodity products, and when the value of finished goods are very low, as in nuts and bolts. If your process is either one of the first two conditions, the make-to-stock system will minimize shortages and stockouts when real demand arrives. If you have the third or fourth condition, you won't be heavily penalized with obsolescence costs or holding costs respectively in case you overstock. The make-to-order system builds according to actual demand, orders, bookings, or takt time as we have learned earlier. In theory, this system won't produce stocks as all outputs are consumed or sold immediately or in a very short period of time. If you have short lead times, high capacity, high output variety, or high value of finished goods, you would want to adopt the make-to-order system to minimize your holding costs and risk. A service factory is always a make-to-order system, since you can stock up customers. Barbershops can't produce haircuts in advance. Your system needs to adapt as your process changes over time. For instance, as you cut lead times and improve capacity, you may want to switch from make-to-stock to make-to-order to reap the full benefits of your process and productivity improvements. Also, as product variety and value added increase, when you move up the value chain or value stream, you're better off with a make-to-order system. Nowadays, you may also hear about push and pull systems. These are nothing but fancy, easy-to-remember labels for our make-to-stock and make-to-order systems. The make-to-stock is the push system since all prior processes and workstations, including suppliers, tend to overproduce and push their outputs to the next process. Every process seems to be pushing inventory down the supply chain, producing according to its capacity, mindless of the takt time or take-up rate of the next process. Conversely, the make-to-order system is a pull system, since every station doesn't process or start processing unless pulled by demand or by the next process. Everybody's pulling everybody else down the line like a train. Let's now try to visualize our two production systems. Let's start with our original 5-station process with their capacities indicated here. Suppose demand is 10 units per hour. Let's see a make-to-order stock case in which everyone tries to produce according to their capacity. See what happens to their actual or throughput rates. This system, which we shall call make-to-capacity, will create costly work in process and finished goods inventory at the end of the line. A make-to-capacity system often assumes a seller's market, a build-it-and-they-will-come environment. A variation of the make-to-stock system, which is somehow better, is one in which everybody synchronizes with the bottleneck as shown here. At steady state, this make-to-bottleneck process will produce only finished goods stocks, but not work in process. Note that both systems will be producing more than the demand rate of 10. Let's now see how our process would behave on a make-to-order basis under the same conditions. There are two ways to actually meet the exact demand or orders. The first is what I call the push-pull process. Here, every process produces the capacity or plans based on forecasts, except the last process or processes which produce based on actual demand or takt time. There are no finished goods inventory as goods are immediately delivered or sold just in time. This can be considered a hybrid just-in-time system with just-in-time delivery but without just-in-time production, since work-in-process inventories are created in the upstream processes. Here the upstream stations are pushing with their capacities, but the downstream stations are being pulled by the market. Now, why would anyone want to do this complex production? For instance, you're making cars or something similar. Your upstream processes may be high-capacity machines, making low-variety, standard parts like presses stamping uniform metal brackets. But your downstream processes are lower capacity, labor-intensive assembly processes that make high-variety car models. According to our previous slides, the first half of your factory would be better off making to stock, while the second half better off making to order. From the customer's point of view, however, this may seem like a pure make-to-order system, since he doesn't see nor care about what you do in your back office. Now let's consider a completely pull make-to-order system. Here, as you can see, everyone produces according to the demand rate of 10 or takt time, and not according to its capacity or the process bottleneck. Notice that there are no work-in-process nor finished goods inventory in this system. Let's take a look at a pull line or just-in-time line in detail. It is a special type of make-to-order system in which all workstations, not just the last one, strictly produce according to the takt time. Here, a workstation will only produce and deliver only if required or pulled by the next workstation, also referred to as its internal customer. Ideally, the parts or raw material supplier of a just-in-time process also delivers inputs according to takt time. The just-in-time line is also known as the one-piece flow, lean system, or Kanban system. It is one-piece flow since there is only one piece or one small batch between each station at any time. Since it minimizes, if not eliminate, work-in-process and finished goods inventories, a just-in-time line is also a lean system if we consider all forms of inventories as waste and unnecessary. Why call it a Kanban system? The Japanese term Kanban means a signboard. In a just-in-time line, it refers to the physical or electronic signal a station sends to its prior station, which tells it to start producing or delivering the next unit. The Kanban is a sort of internal purchase order one receives from its internal customer. The Kanban effectively controls the process flow in a just-in-time line and ensures every station works according to takt or the requirements of its next process. Any line, balanced or unbalanced, can be converted from a push to a pull or just-in-time line. One criticism or weakness of a just-in-time line, as you may have observed, is its low capacity utilization. More often than not, as it produces to demand, most if not all processes and stations will produce less than their capacities, including our former bottleneck station C. The way to get around this weakness is to redesign your process or create a new one such that the line is balanced and every station's cycle time matches the takt time. In other words, the throughput rate of each station is its capacity. Direct labor utilization will be 100%, and work-in-process and finished goods inventory are virtually eliminated. The balanced just-in-time line will be the least cost process configuration.